So today we'll be talking about AI and ML accessories. It's an introduction to data pre-processing and AI methods. This is lecture 3B. We're talking about data processing, images, PCA, which is principal component analysis, and removing outliers from data sets. We'll talk about active learning, talk about compute power requirements for machine learning models. We'll take another peek at RAG, retrieval augmented generation, and large language models. All right. So, introduction to the lecture. I'll begin by explaining how data pre-processing and advanced AI methods impact model performance and reliability. This lecture will delve into both data-centric techniques and advanced AI strategies like RAG and large language models. We'll talk about them a little bit. Optimize model development. Outline of topics would be data pre-processing. It's the importance of cleaning and preparing image data and dimensionality reduction techniques like PCA, which is principal component analysis. We'll talk about this. Active learning is how to reduce labeling costs by focusing on the most informative data and most important data in the data set. We'll also talk about compute power requirements, discuss how large language models demand significant computational resources and energy. RAG and large language models will address advanced techniques like modern natural language processing to improve output quality and mitigate hallucinations. We talked about hallucinations a little bit too. Example here would be mention how principal component analysis, which is PCA, can be used in facial recognition to reduce the number of input features while still retaining key information from the data set, even though we reduce the dimensions and input features. And for identity recognition. To summarize, we'll set expectations for covering foundational techniques and cutting-edge research in AI, balancing practical applications and theoretical understanding. So if we take a look here, talked about how the data needs to be pre-processed before we use it into a data set or into a machine learning model, right? So, data pre-processing, the steps are like one here, the inventory data sources. We look for the data sources first. We said data sources have to be reliable, like government or like a research facility like this. And fix the quality issues in the data. That's in the second step. Third step would to be identify important features. What are the most important features to add to the data set to make our predictions, right? Number 4 would be apply feature engineering, which we did a little bit of it last. I showed you guys a little bit of it last lecture, right? We did some feature engineering and exploratory data analysis. We looked a little bit at the data and did some charts and saw what's in the data, right? That's feature engineering. Validate results. We have to validate our results, see if they're correct, comparing to the predictions. Repeat or complete. If you're done with the pre-processing, your pre-processing is complete, or we repeat the same process until we get good, clean data that is well processed. All right, slide 2. An example here would be data pre-processing for images, let's say. We're going to see an example here. Some of the image pre-processing techniques today are resizing images, scaling the images, normalizing them, image augmentation, which is in this dog picture. I'm going to show you, explain it to you guys. Rotation, flipping, cropping. We know all this stuff like we can do in tools like Photoshop and stuff like that, right? Photo editing, right? Rotation, flipping, cropping, and then feature extraction, edge detection, and color filtering, right? Awesome. For resizing and scaling for images to prepare them to be trained for a large language model, or let's say for a machine learning model, images come in various sizes. Resizing them to a standard dimension ensures uniform input for neural networks. Like images can be 8 by 8 pixels. Some of them can be 9 by 8 pixels. Some of them can be 10 by 6 pixels. So before training the model or doing anything else, we have to put them all in the same pixel dimensions. For example, here, resizing MRI images, like the ones in hospital and stuff. to 224 by 224 pixels to match input requirements for a CNN medical application. We're gonna make a convolutional neural network. So we have to make all the images in the same size, basically. So that's one of the steps before we train a model. Normalizing also for pictures, which here we'll talk about converting pixel values from 0 to 225 to range of 0 to 1, like we said, scaling from 0 to 1, or from -1 to 1, instead of having these big numbers, right? Talked about how colors and pixels come from in the 255, 255, 255, and RGB is white, right? Remember that? RGB, red, green, blue patterns. So we have to scale also, which we talked about scaling, how to make it, instead of big numbers, make it between 0 and 1, or -1 and 1. This speeds up the training process and reduces the chance of overfitting. We also talked about overfitting and how we need to avoid that, right? An example here would be an image classification. Normalized inputs can stabilize the gradient descent, improving the model's convergence and performance. Another thing is data augmentation. We talked about also. It introduces variations just like rotation, flipping, brightness change, like the stuff we do with pictures usually. When we edit our pictures or something, right? We do all these things and apply filters and apply this and that. So this is part of data augmentation. An example for that would be a medical imaging data set can be augmented by flipping images horizontally or applying slight rotations to increase robustness against oppositional variances. I'm going to show you this in the dog. Oh, Avi's here. Oh, awesome. Let me go.
I don't think I was sleeping once.
You were sleeping.
Sorry, I just started.
So we just skipped one slide for you, Avi. Let's, I'll go through it again quickly. Talked about data pre-processing and how we need to pre-process the data before training any models or anything. Like you can see here, first we choose the data from the inventory from a reliable source, right? Fix quality issues, identify our important features to go into the model, drop the features we don't need, apply feature engineering, which I showed you guys using ChatGPT last time. We did some of that, and validate the results, see if the results are good. Repeat or complete. Repeat this process or complete your pre-process. That's to summarize slide 1. We went on to slide 2. We're going to talk a little bit about pre-processing for images. See how like we can scale images, right? From if they all have to be the same size. So here we can scale them to like 224 times 224. All images have to be same size. Normalizing, converting pixel values from 0 to 225 in a range between 0 and 1 and -1 to 1. Speeds up the process. Augmenting, which is getting rotations of the picture, different positions of the picture, right? And then feature extraction is like edge detection, helping identify prominent structures in the image, like the edge of the image, the ear of a dog, the face of a cat, the nose, this and that. These very minute things, right? For example, canny edge detection can simplify an image of a road scene to highlight only lane markers for autonomous vehicle training. Let's take a look at this here. So you guys can see here, this is an image data set. It goes in batches, like the images don't go in right away. They go in batches, right? You know what I mean? Like batch by batch, they don't get trained all together. Do some image augmentation, which is like this here, right? Transform the batches and train a CNN on the batches. Convolutional neural network. See here, this dog picture, we put it in multiple rotations and positions, right? Because a dog might be sitting like this, and that's the only picture I have of him. But I want to see him I want to train the model on multiple positions. dog has to be in multiple positions. Not just for the dog, for any other picture, right? So this is data augmentation. We're doing some processing on the data, augmenting the original. This is the original picture of the dog, but this is the only position we have for this dog. So we make all these augmentations, rotate, crop, flip, do this and that until we have multiple images in multiple positions for object detection, right? All right. Slide 4, principal component analysis. So it's used to reduce the complexity of a data set while retaining essential information, right? So it reduces the dimensions in the data set, it reduces a lot of complexity. It's called principal component analysis, PCA. Principal component analysis identifies directions along which a variation of data is maximum. Like when you have two very maximum values and very minimum values, you want to get rid of these and dimensions, right? So we use principal component analysis to do that. Its application in image processing, like image compression, for example. It can reduce the file size of an image by focusing on the components with most variance. So if an image is like two megabytes, we use principal component analysis to reduce it down to like 1 megabyte, let's say, right? We reduce a little bit of the unwanted things in it, unwanted pixels, unwanted borderings or some stuff like that. It reduces the size and makes the training process much faster and easier, right? Noise reduction also reduces the impact of less relevant features, which we call noise in machine learning. The features that we don't need in that it's called noise reduction. So we get rid of the features we don't need, which we call noise, which helps models learn underlying patterns better. It makes the model learn the patterns in data much better, right? Data visualization also helps, allows for the visualization of high dimensional data, maybe with 1,000 features. Some data sets have thousands of features, in 2D or 3D analysis. Example of that is applying a principal component analysis to high dimensional MRI images, like the ones in hospitals we talked about. It can reduce each image to a handful of principal components, facilitating faster processing and analysis. To summarize, PCA is widely used for dimensionality reduction, reducing the dimensions in data, making it easier and manageable for models without losing significant information. Like, reduce the complexity without losing the important information in the data set. Principal component analysis. Let's take a look at this. You guys can see here, see how this is like in the 3D plane, right? This could be like a 3D data set plane or something like that. And here it's 3D, 1 dimension, 2 dimensions, 3 dimensions. You see how it flattened it to 2 dimensions here? It got flattened to 2 dimensions. This is just to show you how it works in like the graph system. This is 3D, it got flattened into 2D. And it didn't lose any of its features or anything. So when it goes into the data set and gets trained by the model, it won't lose a lot of its features, right? We just reduce the dimensions to make things faster and quicker for it, right? And less complex. All right. Removing outliers in data. Outliers are like extreme values, like too small values or too minimum, like too small or too big, you know what I mean? Let's say the column has values between 1 to 10, right? I have a value that's like a 0.2 or something, and then a value that's 15 in between these values. So I get rid of these 2 values too. So the data can be trained better, right? Purpose of outlier removal here. So common methods for that also would be a z-score, which I'm going to talk about, inner quartile range, visual inspection, scatter plots, box plots, algorithmic techniques like isolation parse and DBS scans, density scans. So the purpose of outlier removal, outliers can introduce noise. So they cause noise in the data when there's data that's too extreme for the model to be trained on. It reduces the robustness also of the model. when we have outliers, and it increases the chance of overfitting, which we want to avoid. We always talked about avoiding overfitting and underfitting, right? Techniques to remove outliers are like the Z-score. It measures how many standard deviations a data point is from the mean. Points the Z-score greater than 3 are typically considered outliers. So I'm going to show you a picture. Using the inner quartile range, which is this picture here, it identifies the outliers using this formula right here. We have right here. And algorithmic approaches, just like isolation forest, which is this picture, and DBC scans, which is density scans, detect outliers based on clustering behavior and isolation principles. An example for that would be in a data set of patient, patient blood pressure readings. A few extremely high or low values might be errors in the data entry, right? So we have someone who has extremely high, like it was put in as an extremely high blood pressure, for the other guy was extremely low. It might be a mistake from someone who was putting in the data or something, you know. That's an outlier. Removing these values can lead to more accurate diagnosis prediction. To summarize, outlier removals ensure the model isn't misled by extreme values that don't represent the general data distribution. Let's take a look here. So did you guys take statistics at all? You know the interquartile range, right? So this is a box plot. It gives us the max value in a range. The upper Q3 here would be the 75th. The median would be the 50th, right? Lower quartile will be the 25th. And minimum and the minimum here. These are the whiskers of the box plot, right? So the IQR, which is the interquartile range, is a way we can find outliers. So we get rid of the outliers in the max here and the minimum here. You know, gives us better values and removes the noise. And for the Z-score, you can see here, this is a normal distribution, right? So these are usual values, not unusual, right? These are moderately unusual, but at Z3 and Z negative 3, we have outliers, right? We have very extreme values that we want to get rid of. If we make like a normal distribution plot for one column or something to see the values in it, right? Just like the petal width we talked about last time or something. We want to see the values. So we have the values going up and down like this for distribution. At Z negative 3 and Z3, we can see that, you know, these are very extreme values that like are outliers. Here it's in the total negative and here it's in the total positive. So try to get rid of these. An algorithmic approach would be these density forests right here. You know, if it detects like these dark blues are anomalies that have to be avoided, they look like trees, like a forest, you know. And this is a normal data point. These are normal data points, and when it gives you like this kind of distribution, you know, the dark blues are anomalies that we want to get rid of. That it's an outlier, and the lighter blues are not outliers. We don't want to get rid of. So these are types of graphs we can take a look at. I'm actually going to show you guys an example because I'm going to train a model today for you guys that's going to predict the flowers like we talked about last time, right? I'm going to show you how it's going to predict this flower and this flower. It's going to be good. You guys are going to like it. All righty. So active learning, another accessory, machine learning. Active learning is a machine learning approach used when acquiring labeled data. It's expensive or time consuming. I can't get data from anywhere, you know, because it might be too expensive for me to obtain that data, or, you know, it's time consuming to make it or get it. For instance, if we need medical experts to manually label thousands of medical images for a cancer detection model, right? To manually do that, the cost and time investment would be very high. Active learning solved this issue by only selecting the most informative data points for labeling, right? Ensuring the model learns effectively from fewer examples. So we have few examples and we want to train the model to detect these images, cancer images. We don't have enough data. It's expensive to get from outside. It's time consuming to make, right? So we use this active learning technique, right? It reduces labeling costs, increases models efficiency. Some of these techniques would be something called query by uncertainty. The model selects data points it is least confident about, and a binary classification. For example, identifying if an image contains a dog or not. The model's confidence for certain predictions might be like close to 50% for probability. An example would be a model analyzing X-ray images for detecting pneumonia, which is a lung disease in the lung, right? And it might struggle with some of the images showing predictions around like this, it's 50%, pneumonia or not pneumonia. These images would be prioritized for labeling by a radiologist, even if they give you 50% certainty. And there's another technique called query by committee. Multiple models, each trained on the same data set, vote on a new unlabeled data points. If the model disagrees significantly, it indicates high uncertainty, which we don't want, of course, and the data point is labeled. For example, in text classification, we give text to the model, and it's supposed to classify that text. Committee of models might be asked whether an article is biased or unbiased, right? If one model says biased and the other says unbiased, it shows disagreement, making it a good candidate for later, right? False. Real world examples would be medical imaging. Active learning can prioritize labeling of medical images like MRI scans. You guys know what MRI scans are? For cancer and stuff like that, right? At hospitals. Where it's unsure if a lesion is benign or malignant. It doesn't know if the cancer is benign or malignant. So benign cancer is a good cancer, and malignant cancer is the one like when you remove it spreads again in your body. So, hopefully no one gets cancer at all. Radiologists are consulted only if there's ambiguous cases. Therefore, it's optimizing their time. So that's where active learning gets used a lot in medical imaging, and also in speech recognition when developing a speech-to-text system, which is like Siri. You talk speech and it gives text. It's called a speech-to-text system. Active learning can focus on labeling speech clips. Active learning, that's what it's working on. Where accents or background noise make transcriptions difficult. So it's difficult also because people sometimes have different accents, especially for English. We all have different accents for English. So in these cases, you have to train it on different accents too, right? The voice command. Take a look here. You can see the loop, right? Active learning. We append the newly labeled data. Yeah, the new labeled data. It gets trained on it, train the model on the labeled data, right? You can query through that. You know what a query is, right? Query is just like searching for something or on Google. That's a query, right? Use acquisition function to select example from labeled data and then annotate and then repeat. It's called the active learning loop, right? And here we can say, too much unlabeled data. It doesn't know what to label and what not to label, right? That's why we use active learning. So active learning gets into the way. It does the labeling for us. A valuable labeled data set gets produced, and a better model gets trained, right? Because it's labeled data. It's easy to train. All right. Next slide. Challenges. So, like we said before, making these models consumes a lot of energy, right? It's computational energy from the computer, which is electricity. So the challenges with high compute needs, modern AI models can often require large-scale compute resources, right? These are a lot of resources, which becomes a bottleneck and a problem and a milestone for training and deployment, right? Optimizing strategies like model pruning the model, removing unnecessary parameters from the network to reduce size and complexity. Like pruning a tree, getting rid of the excess leaves and stuff. It's the same thing, we get rid of the unnecessary features and unnecessary complexities, which is what we call model pruning. It's like cutting leaves out of a tree, like a very dense tree, and you reduce the leaves a little bit, right? Optimizing strategies, like we said, model pruning, quantization. It converts high precision weights, like 32-bit floating points, to lower precision weights, like 8-bit integers or something, to decrease computational load. That's another way. Quantization, reducing the bits of computation. Distributed computing, spread the workload across multiple GPUs. So I have 10 computers in the room and one master computer, so I can spread the model training on all 10 computers instead of using one computer, right? It gets distributed, and the load gets distributed on all 10 computers and gives us a better, faster training. Speeds up the training and reduces the cost, right? All right. An example would be Google's use of TPU, which is tensor processing units, for training large language models like GPT-3, which use unfeasible on standard GPU setups. So our regular GPUs on our computers can't really train these very large models. So they use this distributed computing technique to do that. Instead of one computer taking the whole load, I have 30 computers, so I distribute it throughout all 10 computers. To summarize, understanding and optimizing computer power requirements is critical for scaling AI solutions. Let's take a look here. So pruning, like we talked about, one of the pruning techniques would be neuron dropout, right? You see here, it has all its neurons in this model, right? We pruned a little bit of them, right? We got rid of some of them. So instead of 4 in this layer, we have 3. Instead of 3 in this layer, we have 2. So it reduces the complexity, right? And gives us good results also. You guys can see here, amortized hardware and energy costs to train AI models. See, the energy cost is increasing, right? It's going up to the tens of millions here. Like training GPT-4 here was in tens of millions, like I told you guys before. Gemini is Google's new model. Took a lot of energy, see up to 2024 here. And you see how it's increasing, right? The more complex and more sophisticated these models become, the energy cost increases too. Like you guys can see, it's in the tens of millions, and it's going to be in the hundreds of millions. Up there, we can see also the energy demand is going to be very high for training AI. See how the energy demand is very high just to train AI? Transmission, data centers, everything else is like, in the lower part. But training AI is like, top of the roof, right? It's crazy. It's a lot of energy, right? Yeah. All right. So slide 8. Slide here. So we talked about large language models. Defined just like GPT-3, we have BERT, we have T5, we have Claude. They use deep learning on large data sets to generate or interpret text. Deep learning. Key characteristics are like contextual understanding. Large language models can understand context from what you're writing or what you're saying. Transfer learning, like we talked about, getting a pre-trained model and adding some features to it instead of training one from scratch, right? And self-supervised learning. It trains itself and corrects itself, basically. An overview, large language models like GPT-3 can generate human-like text and perform various natural language processing tasks, such as summarization, translation, and question answering. We used this before, and you guys use it, of course. They work by having been trained to learn the probabilistic weightings of relationships between words and sentences. So they know the relationship between words and sentences and the context, right? So they can predict not just the next word, but the next block of words, right? Like when you're texting on your phone, you see how it predicts words for you up there? That's a large language model trained on that. It knows what, now they're making it to predict the whole sentence you're gonna say next, maybe the whole sentence you're gonna say tomorrow. It might predict that, like literally, it's crazy, right? This breakthrough component of the technology is called attention, or multi-headed attention, like in Transformers, we talked about these. And it's a key component of transformer models, right? Characteristics would be contextual understanding. Large language models can capture relationships between words and sentences, so they can understand the context you're talking about. I am drinking this in the morning. It's gonna give options, orange juice, milk, this or that, right? It predicted what you might say, right? It knows the context, making them effective at understanding long passages of text. And then you have transfer learning. It's pre-trained on vast data sets we talked about, pre-trained models, right? These models can be fine-tuned and we can go like make a little bit of tuning and adding stuff to it on specific tasks with smaller data sets. Leverage the knowledge gained during pre-training. And it's self-supervised training. So the models are trained to predict masked or missing words, enabling them to learn linguistic patterns without label data, which is amazing. An example of that would be using GPT-3 for text summarization and legal documents to automatically condense lengthy contracts into bullet points. So like, you have like a 70-page contract, give it to GPT-3, summarize this for me, tell me what you think. It helps you, that summarizes everything for you. To summarize, large language models are transforming how text-based applications are built, offering high flexibility and contextual understanding of diverse data tasks. Take a look here. So like here, you know, if you're training from scratch, right? Let's say you're making something to classify a model to, it's gonna classify car, truck, and bicycle. You're gonna have to train that from scratch because you don't have a model that's been trained on that. While in transfer learning, we talked about, right? It's trained on cat and dogs, but I want to add truck pictures to that model, right? It's already trained on cat and dogs, a convolutional neural network for cat and dog images, and you know, I want to add a new task to it, which is trucks. Yeah, I wanted to see if it has, you know, trucks and cars. So we just add the new car and truck images to it instead of training something from the beginning from scratch, right? Also, let's take a look here. You guys can see some of the most prevalent large language models. GPT-4o, that's the newest, you know, made by OpenAI. You can see the pricing here, their quality is very high, speed. Also Gemini made by Google here, Gemini Pro. It can tell you its context window and how many parameters it can deal with, right? Its price and training. All these things here. See, its price, quality, speed. We also have a Command R. It's another one. Llama is made by Facebook. It's actually not a bad one. I haven't tried it before, but I heard it's good. And there's Mistral. I think Mistral is made by IBM. I think so. I don't know. Or Mixtral. I don't know which one of them is made by IBM. But this is, you know, to show you some comparisons between certain large language models. All right. So some challenges with large language models. Common issues are high compute costs, of course. We talked about that. Very high compute costs. Bias and ethical concerns. We talked about how biased and ethical concerns can be there, right? Model interpretability. How to mitigate these problems with efficient fine-tuning of the model, reducing model size with knowledge distillation. Right, we'll talk about these. So the high compute costs, training large language models can be prohibitively expensive, requiring extensive hardware setups or cloud resources, right? Like we need big, good hardware, strong hardware, and a lot of money for the power, of course, the energy. Bias and ethical concerns. Large language models trained on biased data. We talked about biased data before, right? How data could be sampled biased, you know, may generate prejudiced outputs, you know, outputs that are prejudiced, unfair, or imbalanced, right? Many large language models were trained on data publicly available on the internet, which they mostly get it from the internet, regardless of copyright, leading to direct copying or derivative work without citation or royalty licensing. So you might bring out someone else's work from online, you know, and that's going to cause copyright problems, right? Model interpretability, understanding why large language models make certain decisions is difficult. making them less suitable for transparent decision making. So to mitigate these things, we can do what? Efficient tuning, using parameter efficient tuning methods like LoRa, which is low rank adaptation, can help reduce resource usage. Knowledge distillation, training smaller models, which is like we call them student models, using the knowledge of a larger model, teacher models, to create lightweight yet effective versions, which is basically like knowledge distillation is like let's say I come to you, rub my head into your head, and my knowledge gets into your head, right? Something like that, or rubbing a book to your head and the knowledge gets transferred to your head. It's called knowledge distillation from the teacher to the student, right? Something like that. So an example would be the use of TinyBERT, which is a large language model, a distilled version of BERT in mobile applications to enable device natural language understanding with minimal computational power. It focuses on one task only from that large model. So we call it a student model, right? So if the large model can do 100 tasks, we can train only one small condensed one to do one of the tasks, the large language model, right? Instead of using the large language model and computing and having like a lot of computational resources and energy costs. To summarize, addressing these challenges is essential to responsibly deploy large language models to real-world scenarios. Take a look here. See here, teacher distilling into student. It's a smaller and denser model with fewer parameters, faster during inferences, and prediction quality close to the teacher model. It's just compressed and condensed, like fewer parameters, called knowledge distillation. Some of the challenges, like you said, computational resources and infrastructure, data collection and data process and pre-processing, toxic or wrong data generation, training time and the iterations, overfitting and generalization, environmental impacts, like we said, the energy, a lot of energy is needed. So these are some of the challenges with large language. All right. We talked about retrieval augmented generation, which I don't want to talk about too much today, but I mean, it combines information retrieval. Like we know how we talked about how a large language model can now, instead of being trained on the current data, it goes out and fetches this data, right? From data sources and data systems. So that's how it retrieves all this data for you. It enhances the large language model by incorporating context from trusted external databases, right? Improving your response accuracy and relevance to the details you're giving it, right? Let's take a look here. So you asking the large language model a question, right? The question is, look, this is where RAG happens, retrieval augmented generation. It's going to this knowledge base or database and fetching that information from it, right? So it goes back to the smart search, gets processed through the large language model and gives you that answer you want, right? So it's awesome, actually. How it works. So to summarize, I would say RAG is a powerful tool for bridging traditional information retrieval and generative capabilities, reducing hallucinations. We talked about hallucinations, how the model can give you wrong data or bad data, right? Or bad responses, and improving reliability of the large language model. We talked about RAG. All right. So integrating RAG into the large language models has a big benefit, which is it can be integrated with large language models to enhance response accuracy. You have good, accurate responses from the large language model, and reduces hallucinations, which we don't want. An example would be using RAG for more accurate and fact-based conversational AI, right? So an example would be a RAG large language model integration, which every large language model now is integrated with RAG capabilities. The large language model can answer research-related questions by retrieving papers from an academic database and then generating a synthesized response for you. So that's what RAG does. It's going to go to that academic database, bring you that response, synthesize a good response for you, and then give it back. So to summarize, RAG enhances the performance and trustworthiness of a large language model and reliability, making them more suitable for knowledge-intensive applications. Let's take a look here. So this is how RAG controls hallucination, right? You make your query or your prompt, ask ChatGPT something, right? It goes through the ChatGPT's memory, right? Query, the user, it wants to see what the user's intent is. So here's checking for context in the entry. Embedding generation, like we said, embedding is to tokenize what you put in into little numbers and stuff, so the computer can understand it. Goes through something called a vector database, chunks it up. These chunks go through an anti-hallucination algorithm built inside the RAG algorithm, called anti-hallucination algorithm, which is this one. And then returns it to you in the prompt, which you read here as a response, right? So integrating it into a large language model, as you can see here, I'm the user here, ask the chatbot, right? This is step one. Step two, it goes to search for that information through the database and online sources, right? Three, it brings it back to the chatbot, processes it through the large language model, gives it back to you. Pretty straightforward, right? Pretty straightforward concept. And then F1 scores here for hallucination detections. I'll give you some examples here on how percentage of hallucinations with each one of these models, right? We can see that this one is doing the best. The GPT 3.5 Turbo Zero Shot at 29.7. This was just like a study, hallucinations. This one's not doing so well, at 60% hallucinations, right? Like this Ragas one. And we can see the best one doing the best here is the one that has the 30% hallucinations, right? And this was an older shark, but it just, to give you, you guys get the idea, right? Like how certain models can have less hallucinations than others. They were made well. All right. So case study, made a little case study here. I'll go through quickly and then get to show you guys training the model. The scenario is an organization wants to build a large language model to automatically classify customer emails into technical support and general inquiry. The labeling data is limited. We don't have a lot of labeled data, and manually labeling thousands of emails would be time consuming and costly. Yeah, it's crazy, right? I'm not gonna make you sit down and label every email. It's crazy if there's like 1,000 emails. Solution would be active learning. We applied to optimize the annotation process by only labeling sentences where the model was unsure, right? Process of implementation, initial model training. Our large language model was initially trained on a small labeled subset of emails. This provides the model with a basic understanding, so we have a good base because it was trained already on some emails. Identifying the uncertainty, the model analyzed a large set of unlabeled emails and identified sentences where it was least confident. And that's what we focus on, the parts where the model was least confident. Example would be a sentence like, I need help setting up my account, but I also have some questions about pricing. It could be classified as either technical support or general inquiry, right? But using that less confident technique puts it into its place and annotizes it. Prioritizing for human annotation. The model prioritized these uncertain sentences for human annotation. Human annotators reviewed these sentences and labeled them appropriately. So we trained the model. The large language model was retrained on a newly labeled data set instead of the old data set, incorporating the additional information from human annotated sentences. So they made them, they had to go back and label them manually anyways, because they needed that data, right? So they trained another large language model in this case. So just to summarize, by leveraging active learning, Organizations can make the most limited annotation resources, improving overall model efficiency and reducing development costs, which is the target always. You can take a look here, see how he's. See, the computer here is happy with better annotated, responses. Here it's like you just put in a random prompt or random question. You don't put enough context. So active learning, what it does is it smooches small batches of that prompt, and then this expensive retraining is not needed because we made a better prompt for the prompt. So also always put good context in your prompts so that ChatGPT can be happy, like you see I see here, right? So also total cost of training the model versus its accuracy is it increases. The more accurate the model is, the more the training cost is. You guys can see it here, right? The more accurate the model is, the more training cost is going to be. Just like, the more advanced the model becomes, the more the training cost becomes also, and sophisticated. All right. So to summarize the lecture here, future directions for LLMs and RAG, areas of future research, more efficient training algorithms are going to be made, much more efficient training algorithms, improved bias mitigation strategies are going to be made, advanced RAG techniques for domain-specific applications. So this is all advancing by the day. That's the future of RAG and LLMs. So efficient training would be researchers focusing on developing lighter models that offer similar capabilities of the large ones, using lower adaptation sparse attention rate. So making smaller models that can do the same things the large models make, but with lesser cost and lesser space, right? Bias mitigation, we talked about that. Developing more robust strategies to identify and counteract biases in large language model training data. Advanced RAG techniques will be coming out. Building RAG models that are optimized for specific fields, like specific fields for these models. Law, medicine, by incorporating high specialized retrieval methods. To summarize, the future of large language models and RAG make them more efficient, reducing biases, and refining their application to specialized domains. So making models for specific domains, basically. Not for everything, like ChatGPT. I make a model specially for medicine, focus on medicine, you know what I mean? And asking medical questions, answering medical questions. A model that's focused on law only, you know what I mean? Stuff like that. Awesome. So this is for our lecture. Let me train this model, show you guys the process here today. So I asked ChatGPT to give me the same library, the flower library, right? And I asked it to take in sepal length, sepal width, petal length, petal width as inputs for the model. And the target is going to be the species. I want to know what species it is. I asked it to train the model, test its accuracy of training set and the test set. Create 6 random inputs to fit into the model for inferences so we can see if it worked good or not. Calculate the classifier evaluation metrics to see if the classifier did good or not. Graph a confusion matrix, which is also to show us if it did good or not. And graph predicted versus actual values to see if the model did good or not. Right? So we'll take our first cell here. We'll run it. Gave me this cell first. And we'll run it in this cell, Jupyter Notebook. So as you guys can see, I imported a lot of libraries here. The iris. I'm going to import train test split, standard scalar, right? Let's have this one. Okay. Here. So this is our data. Right? We're gonna be making a logistic regression model, which is gonna classify these flowers in their three types: Setosa, Virginica, and versicolor. There's three types of flowers, right? So I loaded it first. Next, we're gonna create the classifier model. See here. So X is gonna be our features that are going in, the future features, all the columns. Y is the species column, target column. We're gonna split it, like we said before, right? Split it into data, training data and test data. Remember that? We split it into training data and test data, right? So I gave it test size as 0.2, which is 20%. So it's gonna make 20% of the data for testing and the other 80% for training data. Random state is 42. This is what most machine learning engineers use. Always put this as 42, right? We're gonna be using a logistic regression model, which is gonna use 200 iterations. It's gonna go through the data 200 times. That's what I'm specifying here in the code. And I'm fitting the training data first to train the model. So we're gonna run this cell. Ran successfully 200 iterations through the data. Next, I'll test the accuracy of the training and training set and test set. This is gonna show us how accurate the model did. Ready? So the model did 97% accuracy on the training and 97% accuracy on the test, which is perfect, you know. There's no overfitting, there's no underfitting, right? If this was overfitting, the model would have done really good here, like 97%. And then with the test data, it would have done like 25% or something. You know, that's overfitting. So the model learned it well, but can't work good with unseen data. So we looked here, 97%, which is really good, you know, for the accuracy test. Now we're gonna be making some inferences. Here, I put some numbers in for it. Made model.predict, used our model to make our prediction, and it predicted it as a Setosa. You guys see this? Predicted it as a Setosa. It worked. It's 97%, you know, accurate. And let's say I change these values a little bit up here. See these values? 5.5 for the petal width, 3.5 for the petal length, 1.3 and 0.2. Let me change these a little bit and see what it gives us. Let's say 4.5. Let's say 3.2. This is 2.5. So 1.5 or so. Yeah, predicted also as Setosa, but I want to make a random generator here. So this is gonna randomly generate some of these numbers for me. See? So it made 6 predictions here using these as low values and these as the high. And first it predicted Virginica, versicolor, Setosa, versicolor. Let's run it again. It's gonna do 6 more random values. See how it's changing? but it's predicting it right. See? It's a very accurate model, 97%, right? So I can go change on these values here to see one example. This is 6 examples. So let's say here it's low is 4.3, high is 7.9. Let's put here 6. Put here 4. And it predicted it as a virginica. See this? I just changed but it's a very accurate model. It's predicting these flowers correctly. This one, I give it to make these random. I use this random function here to generate between these two values. So you see, every time I run it, it's gonna give us different values. See? Amazing, right? So I trained the first model in front of you guys, running good, 97% accuracy, which I was surprised actually to get this much accuracy on, one repetition. So I'm gonna graph a confusion matrix, right? I mean, first, I'm gonna make a classification report, see how the classifier did. Right here. So the precision is 1, which is 100%. Guys, 100% precision. Its recall is 1, 100%. The F1 score is 1. You always want it between 0 and 1. And the higher these scores are, the better the classifier does. Between 0 and 1, right? It's awesome, right? So this gave us a report. Here I asked it, cell 6, to graph the confusion matrix. Let's take a look at the confusion matrix. It's a model that did really well, actually. Surprising. See, you can see here. It had 10 virginicas, which it really predicted as virginicas. One mistake here. It thought it was a virginica while it was a versicolor. Only like one mistake. So I think that's where it went to 97%. Here it gave us Setosa also. It did it very well. 10 Setosas, wow, really Setosas. Really good. Model's doing good. Then I say graph the predicted values versus the actual values to see how good the model is also. Some of the stuff we can take a look at. See this linearity? Shows the model did very well. No curviness, no ups and downs. So it did really good on the predicted and actual values, right? So he asked it what? Generate any other graphs and metrics to evaluate the model. So classifiers have multiple graphs and metrics to evaluate, see how good it did. One of them is this, it's called a rock curve. Gonna get the rock curve. See also how well it did. But here there is no curve and it's totally linear. So everything is everything is straight. Shows us the model is doing perfect. At 97% accuracy, that's very good for a model like this. And this is a precision recall curve to see how precision and recall go against each other. Here. Shift enter. Totally linear, nothing like bad. Everything went fine. Doesn't have any zigzag or anything. Tells you this model did really, really good also. And this is a feature of importance. I'm not using a random forest, so I'll skip this. Pair plot here. See all you checked out a pair plot before. Let's install C1 first. Pair plot is showing us all these features against each other. Sepal length, sepal width, petal length, petal width. You can like go, let's say I want to compare sepal width to petal length. So I go here it is. All three kinds. This is where I can make some of my, analysis and look at different correlations and variances. Pair plot. Right? And then the learning curve to see how well it did during the training process. See how it generated all of this for me? See all this code? 10 years ago or something, you would have, had to sit down and type all of this. It might have taken months or something, but these days it's, if you know how to use this technology, it's amazing. Right? This is our learning curve. See, the model was struggling a little bit here, at its 80th iteration or something. And it started converging until they met at this point, and the model was completed its training to perfection. You guys can see here a little bit, it suffered a little bit here, did not a little bit, until it converged here with the training score and the cross validation score. Shows us the model did a little bit, took a little bit of a curve, but it reached its optimum point right there where it trained really well. So this is one of the things they do in training models. This is a classifier classifying three types of flowers, right? So if we want to go back up here and play around with other values or something, right? Let's see if I change the iterations here. So like you said, tuning, right? I'm gonna go back and make some tuning. I'll change the iterations to, let's say, 250 and see if it changes the accuracy of the model at all. Run this cell, run this cell. Nope, it didn't. Let's say 300. It's still at 97% accuracy. Let's change this to 300 iterations. Oh, still at 97%. Wow. Let's say 100 iterations. Maybe it can give us higher accuracy. Still not bad. Insist on 97% accuracy, I guess. Let's say 400 iterations. So, wow. I guess this data is very clean. Yeah, it's doing pretty good on every kind of iteration, which is good. It has 97% accuracy. We tested it on some of this, so if we change these numbers a little bit, it might give us a Setosa. If we change it again, it might give us a versicolor, which is amazing, right? See, got my precision recall F1 scores. See how good the model did. They're all 1, which is like 100%, which is good. A little variation here with the Virginica or something. 91, which is still good, 91% on the precision. F1 score is another metric. It did 95%, which is really good too, And for the accuracy, like I said here, it gave us, this is called the classification report method. And we imported it up there. So it gives us a report on the whole classification model training. So this is a model we just trained right now. It classifies into 3 types of flowers. You guys see the process can be easy with these kind of technologies if you know what you're doing and the stuff you're playing around with, which makes it very convenient. See this much code, if I have to go back to debug it, and, make sure there's a comma, make sure there's a parentheses, make sure it's good. No, this gets everything accurately done very well. Train the whole model. We checked for everything here, see how the Setosa did well, versicolor did well, I mean, not so well, because, you know, it made one wrong prediction here, which is, I guess, why it had this little bit of accuracy drop. Where it was a Virginica, but it, you know, it was a versicolor, but it said it's a Virginia. This was one mistake it made, but it's not that big of a deal, because, you know, 97% accuracy for a model like this is not bad at all, you know. Checked our predicted versus actual values. You know, made our rock curve to see if but there's no curve at all, because the model did very well. Made our precision recall curve, no curve either, because, you know, it's straight, totally straight at F1 score on precision. This is perfect, like you see, recall is 1, precision is 1, perfect model. Pair plot to check the correlations, training the model. And we did our learning curve to see where the model, you know, suffered a little bit here at these points, but then it converged and reached its optimum point. And everything is good. And that's a model, guys. That's the model I just trained for you. And, you know, next week I'll train another model, show you guys. But it's going to be a model that from a CSV file from our desktop. So I'm going to have maybe in the medical lecture, the one for AI for medicine, I might train the model that shows cancer types. We hear classifier for benign and malignant, good cancer, bad cancer, cancer, no cancer, right? I might train that for you guys, and we're gonna take a look at it. So the quiz starts at 7:15. Take out your laptops and get ready for the quiz. Did you bring your laptop?
Yeah.
Oh, I thought you. Alrighty.